Good afternoon and welcome back to Dr. Logic Awkwardly Does Logic. In this video, I'm going to do the first of the slightly more complicated rules for quantifiers in our proof theory. This is the universal introduction rule. Think about when you are allowed to make a universal statement. Now, if you're only talking about a small set of things, for instance, 3 books, then if I can say the first one that it is a book, and the second one that it is a book, and the third one that it is a book, you might think, okay, that's what you need in order to be able to say everything is a book, assuming I'm only talking about those 3 objects. But it isn't quite that easy. Instead, you would need to be able to add something that says, and there's nothing else. So not only am I only talking about these 3 objects, there aren't any other objects that I could be talking about. So you don't want to have to kind of do an enumeration of every single object and say it has this property, the next one has the same property, etc. Particularly if you're dealing with an infinite domain, because you're not going to be able to do that. In fact, the whole point of developing our proof theory was so that we wouldn't have to check every single of an infinite domain in order to determine whether some sentence was universally true or not. So what we will do instead is we will talk about arbitrary objects. So if I have a box and I can't tell what's in it, and I reach in and I pull something out, and there is nothing to distinguish it from anything else in the box, then whatever that thing is, I know everything in the box has to be. Precisely because nothing about this object distinguishes it from anything else. So if I pull it out and it's a ball, then I can be like, oh, look, this is a box of balls. If I pull it out and it's a cat, I'll be like, hurrah, it's a box of cats. And then I will very quickly open the box and let all of the cats out, because a box of cats would not be a very nice thing after probably more than about 5 minutes. So let me actually give you an example to show the sort of thing that I'm talking about. We can only make universal claims when we are talking about suitably generic objects. So nothing that we are saying depends on the particular object that we picked. Now, remember that I said the rule for reflexivity allows us to write down term equals term for any term. So suppose we have a language that has a constant a. The rule of reflexivity allows me to write down that a is identical to a. Now, because a just happened to be something I picked, and if I had picked any other constant, I would have been able to do exactly the same thing. What we want is a rule that allows us to write down a universal generalization of this. So to introduce a universal quantifier and then replace the terms with variables that get bound by that quantifier. So I want to be able to say, actually, for every x, x equals x. And I want to be able to do this by universal instantiation on our previous line. The way that we are going to capture this idea of working with generic objects is that we will only be allowed to do this sort of generalization if the term that we are generalizing on doesn't occur in any assumption that our line depends on. So in this case, this would be a legitimate move because there is no assumptions in this proof. I just wrote down this statement of reflexivity and then I generalized on it. But suppose that I had something like, suppose I assume that B equals C. Now, would you think that I should be able to conclude from that everything equals C? So I'll put some question marks there just so that this gets flagged up as not necessarily a good instance. Intuitively speaking, no, you wouldn't. Because just because I have it as an assumption that this object B is the same thing as this object C, nothing from that allows me to make the generalization, well, that everything equals C. In fact, we could easily write a domain. Let's have a domain that has, I guess that must be a squirrel. It was going to be a cat, but it's not. And a giraffe. Now, we could assign an interpretation that gives B to the squirrel and C to the squirrel, but where D points to the giraffe. Now, in this case, our assumption that B equals C is true because it both picks out the same object, but it's not the case that everything equals C because D equals the giraffe, and the giraffe is not the same thing as the squirrel. So, no, this would be a bad sort of inference to make. So, with this kind of intuitive idea of what we're trying to capture with this rule in mind, let's go ahead and write out the formal definition of the rule. So this is universal introduction, sometimes called universal generalization because we are making a general statement from something more specific. And it says, if phi, with some term tau in it, occurs on line I of a proof where I is less than n, tau is a term, then, and here's the important proviso, this is something that you'll need to check every single time before you apply this rule, provided that tau does not occur in any assumption that line I or n depends on, and second proviso that you need to pay attention to, x is not a variable occurring in phi because you don't want to end up accidentally binding occurrences of some variable that were free in the previous sentence, or previous formula, they're free. So you've got to check both of these things. If these two conditions are met, then you can write for all x, phi with x substituted in for t on line n with annotation for all introduction line I. So the important things to note about this rule, there are two provisos that you have to check every single time before you can apply this rule. Second, we've got our abusive notation here. It's not defined for substituting a variable in for an arbitrary term. However, what we mean by this is you look through your original formula on line I, you find all occurrences of that term, you erase them all, you write down x instead, and then you put the for all x quantifier out front. So our schematic version would look like, okay, you've got some premises up here, and then on line I, you have your formula phi tau, some sort of annotation, you don't know what. Then at this point, I now check, is it the case that tau does not occur in any assumption? You know, if this is an embedded subproof, you have to check each of the internal assumptions that are made. And then double check to make sure x doesn't occur in here. If it does, just pick a different variable for your quantifier. But if both of those are met, then I can write down for all x, phi of x, where I replace all instances of tau with instances of x. And this is for all introduction on line I. So just to repeat the two proofs I had earlier. So this is the reflexivity of identity, says that A equals A. Then I can write down for all x, x equals x. I've replaced every occurrence of A with this x. And I can write that down for all introduction, line 1. The way I can do this is that A does not occur in any assumptions that either 1 or 2 depend on, because neither of these depend on any assumption. And X does not occur as a variable in line 1, so I can introduce it in this way. I'm going to make my scope line a bit shorter. If I have some assumption here, A equals B, and then here at line 2, say I want to do universal introduction on A. So first I check, does A occur in any assumption that line 1 depends on? Immediately, I'm stuck because line 1 is an assumption. It depends on itself. A occurs in this assumption. Cannot do any universal generalization on it. So if I wanted to do for all x, x equals b, I can't because condition 1 is violated. Ooh, how about I do one more? So here I again have an assumption, except this time the assumption is that A equals X. So now I want to know, could I do universal introduction on line 1 with, again, substituting out constant A? Well, no, for the same reason I couldn't do it here, but also no, because X occurs in our assumption, in the formula that we were going to be generalizing on. So this one doesn't work because neither condition, neither of the provisos is met. This is one of the rules where the more that you see it used, the easier it becomes. Until you've seen it used a bunch, as you're still trying to kind of work out basic proofs for yourself, every single time, come back to the definition, check that your 2 provisos are met. If they aren't, you cannot use this rule. I will probably continue to stress this over and over again because it's something that trips up, logicians who are just setting off on their logical journey, and it's worth hammering it in. You must check your 2 provisos before you can apply universal introduction. But that's it. So long as you can remember that, you will have no problems whatsoever with this rule. The last rule that we have is incrementally more difficult, but we'll save that for another video. Take care. See you later.